Yeah, so this is work that I did as a postdoc at UCSD before I became a faculty member in Steve Swanson's group, and it was a collaboration with us and all of his excellent students there, and I have the opportunity to share this work with you. So the motivation for this work is that, well, Optane DIMMs are finally here, and that's cool. So the thing about Optane DIMMs, though, and what I'd like to try to convince you of, is that Optane DIMMs are not just slow, dense DRAM. So for a long time, the research community has been investigating non-volatile memory, and they've kind of made this assumption that this is what non-volatile memory is going to be. But it turns out now that we have the actual hardware, it's a little more complicated. So Optane media is slower than DRAM, but this leads to a more complicated architecture at the device level, which leads to second-order performance anomalies, which means that if you want to get the actual maximum performance out of these devices, it's really fundamentally different from programming DRAM. You need to take into account the actual device characteristics. So a brief outline of this talk. I'm first going to go into some background about how Optane fits within the machine and how it integrates with the parts that you're familiar with. Then we're going to talk a little bit about some basics of Optane DIMM performance, just basic device characteristics. And then I want to talk through some lessons that we were able to extract from our experiments investigating the performance of Optane DIMMs. I should note that this talk is not going to include some stuff that's in the paper, which includes an emulation study comparing how Optane DIMMs compare to prior methods of emulation and to what extent we should trust prior research results, and also how we can apply these lessons to macro benchmarks. We took the lessons that we were able to extract and were able to optimize file systems and databases and so forth to show that these are not just lessons that work at the micro level, but also at the macro level. So if that's interesting to you, you can take a look at the paper. And then finally, we'll conclude. Excuse me. So first, briefly, some background about how Optane fits into the machine. So here's a one-socket machine with 3 cores for some reason. So within the socket, each core, because it's Intel, has a private L1, L2 cache, and then a shared L3 cache, which is shared across all of the cores in the socket. Also in the socket, we have 2 integrated memory controllers that are responsible for communicating to the DIMMs that are attached to this socket. Now in a traditional machine architecture before the emergence of Optane, these integrated memory controllers would communicate over a number of channels to a set of DRAM DIMMs. So once we have Optane DIMMs, which you can go out and purchase now and plug into your machines, these Optane DIMMs are going to share some of the channels and can communicate with the integrated memory controller. The operating system has the opportunity to understand the difference between DRAM DIMMs and Optane DIMMs. So when we have it Optane configured in this manner, we call this app direct mode. And so we can literally decide where to put data, if it's going to be DRAM resident or Optane resident. And again, the operating system and consequently the programmer can be aware about the difference of these 2 addresses. The other method that we can use Optane is in memory mode. In memory mode, DRAM is acting effectively as a cache for Optane that's on the same channel. So the OS sees some large pool of what it thinks is DRAM, but is actually Optane cached by DRAM. Optane is the far, dense, slower memory, and DRAM acts as near memory as a direct map cache for the Optane. In this talk, we're going to be talking entirely about the right side of this diagram. There's presumably an equivalent talk that could talk entirely about the left part of this diagram, but this is not that talk. So within the actual Optane device, so to first approximation, this is an Optane DIMM. When the CPU issues a write, the write is going to trickle out from the CPU. It's going to hit the integrated memory controller, and it's going to land in the write pending queue. This write pending queue is gradually going to issue stores back into the Optane device. Now, on the device, this write is going to be received by what we term the Optane controller, that is the device controller, which is responsible for scheduling writes into media. it's going to issue writes in 256 byte blocks, which is important because what we get from the CPU as a cache line is 64 bytes. So the Optane controller is responsible for merging, ideally, 4 cache lines into a single 256 byte block and issuing that block to media. Now, in order to do that merging, on the Optane controller, we have a small cache from the Optane buffer used for merging adjacent cache lines in order to try to effectively use our 256 byte block size. Also, within the device, we have some address translation, which occurs from physical addresses to device addresses. This is the responsible of the address indirection table, or AIT. This table resides in Optane media, but is also cached on device DRAM. The final thing I should mention about this figure, so everything within the red dotted lines is within the ADR, or asynchronous DRAM refresh domain. This is a fancy way of saying that everything within the red dotted lines is guaranteed by the hardware to survive a power outage. That is, if we have a power failure, we're going to have enough stand-up power to flush the write pending queue into the Optane controller. We'll have enough to flush the Optane buffer back into Optane media, and we're going to be able to do this. So once a write hits the write pending queue, the hardware is guaranteeing that it's going to survive a power outage. Okay, so one other thing that's important to understand about Optane from a performance perspective is that, generally speaking, Optane is interleaved across non-volatile DIMMs at 4K granularity. That is, if we have some set of physical addresses, the first 4K is going to reside on Optane DIMM 1, and then the next 4K is going to reside at the other memory controller at Optane DIMM 4, and then 2, and then 5, and then 3, and then 6. So for every 24K that we traverse across the physical address space, we're going to touch all 6 Optane DIMMs, which is the maximum number that we can put on the socket. And at the 25th kilobyte, we're going to circle back to the first DIMM. Okay, so that was a very quick overview of how Optane fits into the machine and how the device actually kind of does its thing. So I want to continue by talking about some underlying performance characteristics of the Optane device. So briefly, what was our approach? Our approach was to do this giant micro benchmark sweep across basically any dimension we could think of. We looked at different access patterns, random, sequential, different types of operations. So if we could do just regular reads, doing regular stores, using CL flush instructions to flush cache lines out of the cache into media, using non-temporal stores that bypass the cache and go directly to media, different stride size, different power budgets, which is configurable on the device. If we're set up in NUMA configuration, and if we have this address space interleaving turned on or off. And once we did this state sweep, we kind of sifted through all of these experiments, and we tried to find things that were interesting and investigated these phenomena. So our second step was some targeted experiments. In total, we ran 10,000 experiments, which totaled across both micro and macro benchmarks about 300 hours of machine time. If you're interested in perusing our data, it's available on GitHub at this address, which is also in the paper. Our test platform was provided by Intel shortly before Optane release. We had 24 cores across 2 sockets. We turned hyperthreading off. On the machine, we had in total 384 gigs of DRAM and 3 terabytes of Intel Optane, which was composed of 256 gig Optane DIMMs. If you're not aware, Optane comes in 3 sizes, 128, 256, and 512. The operating system was Fedora. Okay, so some basics. So the first takeaway is that Optane latency is 2 to 3 times as slow as DRAM, and the 2 to 3 really depends on your access pattern. And this is for reads. So if you access Optane in a sequential pattern, you're getting good performance out of the on-controller cache, so we can do efficient merging and we don't suffer any access amplification, and we get good performance. We're about 2x slower than DRAM. In contrast, if we're doing random accesses, well, we're scattering accesses all over media, we suffer access amplification and we're about 3 times as slow. In contrast, writes, at least for a single write, so long as we haven't saturated anything, the latency is exactly the same. Why? Because the write is acknowledged as soon as it hits the on-socket integrated memory controller. So this is the same both for DRAM and Optane, so we really see no difference in latency unless you've already saturated the device. So bandwidth, what we see is well, relatively scalable reads and not particularly scalable writes. On the far left here, you see DRAM. In the middle, we see a single Optane DIMM, non-interleaved. And on the right, we see our interleaved DIMMs across all 6 channels. So you see that if we use all Optane DIMMs across interleaved, our reads scale reasonably well. We're using all of our DIMMs relatively efficiently. In contrast, the write bandwidth pretty much max out at about 5 threads. At this point, we can max out the bandwidth to all of our devices, and our bandwidth is relatively constant with respect to thread count. So the next thing to know is that access size really does matter within Optane media. So on the left, we have DRAM access bandwidth with respect to access size, and you see that it's pretty constant. It doesn't matter how big your access to DRAM is, it's going to give you relatively the same amount of bandwidth. In contrast with Optane non-interleaved, we have this kind of ramp up to the block size of 256 bytes, at which point everything is stable, because at this point we're using the block size efficiently. So before we move on, I'm going to leave you with a mystery. So this graph stumped us for a long period of time. This is bandwidth with respect to access size on interleaved Optane DIMMs. And in systems, you really expect most graphs to be monotonic. And so this really stood out to us as something extremely weird. What we see is peak bandwidth at 256K if we're talking about, 512 bytes if we're talking about reads. And then we have this valley that hits rock bottom at 4K. And then we come back up as we climb out of the 4K. So, and this is true, or this valley occurs in both reads and writes using non-temporal stores and writes using a store plus a cache line write back. So this really does seem to be something that's fundamental with the performance of the device, and I'll give you the answer to why this occurs in about 10 minutes. Okay, so using all of our experiments and our understandings of the underlying architecture, we wanted to come up with some best practices that we could give as takeaways for programmers who are using Optane DIMMs. So we were able to come up with 4 reasonably pithy pieces of advice. We tried to justify them in the paper and also give macro benchmarks demonstrating that these actually do improve performance, but I'll go over them one at a time. So the first one is to avoid small random accesses, and this all has to do with the media block size. Right, so within the actual Optane microarchitecture, we've got this 256 byte block size, which means that anything that is going to media is going to be in some contiguous block of 256 bytes, and we're going to ideally use this Optane buffer to merge adjacent writes. So if we have small accesses that are smaller than 256 bytes, they're going to be blown up to 256 bytes, and we're going to lose bandwidth. Now, this buffer is used to merge adjacent accesses. So if we vary our working set size, we can figure out how large this on-device buffer is, and it turns out it's about 16K. So even if you don't do sequential accesses, if your working set size is extremely small, you're still going to get good bandwidth out of the device because you're not going to suffer access amplification. And this is basically equivalent to sequential accesses because the sequential access size is again small, or working set size is relatively small. So the lesson 1 is to avoid small random accesses. We get bad bandwidth if we have small random writes or if we have a not tiny working set per non-volatile DIMM that is smaller than or larger than 16K. And we get good bandwidth with sequential accesses because we're efficiently using the on-device cache. So the next lesson is to use non-temporal stores for large writes. So there's really 3 ways for us to write to Optane media. The first is a non-temporal store. This non-temporal store bypasses the cache hierarchy and is issued directly to the backing DIMM. The next way that we can access media is by doing a store and then evicting that cache line or cleaning that cache line using a cache line writeback, or CLWB. And the final way that we can write to media is we can just do a regular store, and eventually it's going to trickle out from the cache into media. So what we see is that non-temporal stores are much more efficient. Why? So with a store plus a CLWB, what we first need to do is we need to fetch the cache line out of media, we need to do the store, and then we need to evict the cache line back into media. And so instead of just doing a write, we're doing a read plus a write. So we're using double the bandwidth in order to do this write. With a store, we have kind of the similar problem, but we have an additional issue, which is that the cache is going to evict the cache line when it decides to, which is according to some underlying cache eviction policy, which is probably not optimized for evicting things in a sequential pattern. So this cache line is going to introduce randomness even if you have a sequential set of stores. And so here's a graph that basically says I'm right, I guess. So you see that non-temporal stores are about twice as fast as a store plus CLWB because we're using half as much bandwidth. And then at the very bottom, you see all of the randomness introduced by simply allowing the caches to do their thing results in terrible device utilization. So again, lesson number 2, use non-temporal stores for large writes. Non-temporal stores are going to bypass the cache, they avoid a cache line read, and they maintain locality. So the next lesson is a lesson about concurrency, which is to limit the number of threads accessing a single non-volatile DIMM. And this really is due to contention at 2 places. We see contention both at the Optane buffer, that is the buffer that resides on the device used for merging adjacent accesses, and contention at the integrated memory controller, the on-socket memory controller. So contention at the Optane buffer has to do with, again, introducing randomness into what would otherwise be a set of sequential accesses. So if we have multiple threads accessing a single non-volatile memory DIMM, they basically thrash on this on-device cache, which means that what would otherwise be a set of sequential accesses that could be merged from some set of 64-byte cache lines into a larger 256-byte block no longer is the case, because all of the threads are putting their own writes into this cache, and we lose the opportunity to merge adjacent writes. So as we introduce threads, you see that, for instance, for reads, we're going to spike up to where we're maximizing our bandwidth out of the device, and gradually as we add more threads, we're thrashing this cache, and we lose the ability to merge adjacent accesses. And a similar phenomenon happens with writes, both non-temporal stores and with CLWBs. So perhaps less obvious is that we can end up with contention at the integrated memory controller. So the integrated memory controller is not generally designed for slow variable latency accesses, which is what Optane is. And so these short queues that are on the integrated memory controller can end up clogged through effectively head-of-line blocking sorts of things. So here's an experiment in which we varied the number of threads per non-volatile DIMM. So we either have 6 threads and each thread is accessing a single NVDIMM, or we have 6 threads and they're all accessing random DIMMs at once. And so what you see is if we pin a thread to a DIMM, both for reads and writes, we don't suffer degradation as we increase the access size. But in contrast, if we have multiple threads accessing multiple DIMMs, what we can end up is we can end up kind of clogging on a single DIMM. And our bandwidth is going to fall down as this bubble basically trickles out into the instruction stream, and we end up with a stall. So this is exactly the reason why we see this valley. So integrated, the IMC contention is largest when the random access size equals the interleave size. So if we have accesses that are larger than the interleave size, every thread, anytime it does some access, is going to spread its access across multiple DIMMs. Whereas if we're hitting exactly at the interleave size, we have these bursts of accesses that all hit the same memory controller and the same DIMM. And because the media is relatively slow and we have reasonably small queues at the integrated memory controller, we see this dip at 4K, which is exactly the 4K interleave size. What's interesting is that, so in theory, if we access things in sequential accesses of 24K, we should be hitting all of our DIMMs evenly all at once. And so if we spread our accesses at exactly 24K accesses, we actually get performance peaks, which you can kind of see right here. And this is, I think, kind of the smoking gun for this is exactly what's going on here with the Optane DIMMs. Right, so the IMC load is fairest when the access size is equal to the number of DIMMs times the interleave size, which is multiples of 24K. So this is our third lesson. Again, if we don't limit the number of threads accessing one NVDIMM, we end up at contention at the buffer, and we also end up at contention with the IMC. So the final lesson that I have is to avoid mixed and multi-threaded NUMA accesses. And really, there's not a lot to say other than that NUMA effects impact Optane a lot more than DRAM. And we didn't investigate this perhaps as much as all of our other lessons, but really this seems to be a second order effect of the slower media. So if we have, and in particular, the read-write ratio of accesses to NUMA becomes much more important. That is, if we have mixed workloads as opposed to pure reads or pure writes to remote Optane, we're going to see this degradation in performance if we have a mixed workload as opposed to a pure read or pure write workload. So to conclude, I hope I've been able to convince you that Optane is not just slow, dense DRAM. It is slower and denser media, but that leads to a more complicated architecture, which leads to second-order performance anomalies. And that means that programming these devices, especially if you want to get the best performance out of them, is fundamentally different. You need to be aware of what you're programming. And max performance on these devices is somewhat tricky. So if I could give you 4 takeaways, avoid small random accesses, use non-temporal stores for large writes, limit threads accessing a single NVDIMM, and avoid mixed and multi-threaded NUMA accesses. With that, I'll stop and take questions. Thank you.
Questions? So, oh, go for it.
Yeah, Tom Talpy, Microsoft. It seems to be all about the blocks, right? It's not a memory device, it's a block device.
So, to some extent, yes. But it's, I guess, kind of. I don't know what else to say other than yes, it's an important performance characteristic of the device.
Yeah.
And even though you have byte addressability and it's DIMM attached memory, you should be aware if you want to take advantage of it.
Yeah, I mean, it's exacerbated by the latency of the device, right?
Yes.
Which changes as it heats up and does various other internal operations.
Sure.
But I don't know. I mean, I congratulate you for boiling it down to such a simple thing, right? But I'm trying to make that observation and see if you agree with it. Is there something else going on under the hood that's responsible for some of this?
I don't know that, I guess you can boil it down to that, but I think that at the programming level, it doesn't manifest itself like that, right? So you need to look at how this trickles out.
Because it's such a challenge for an operating system to schedule its accesses to DRAM, right? Mm-hmm. So I'm challenged by the device, obviously. If you view it as storage, I think you have a lot more control.
Conceivably, but like we've had similar things like this before, right? Where it's worth looking at how you program something, even without looking at storage, right? If you look at NUMA or if you look at multi-threading, right? These are both paradigms that basically the hardware can't get fast enough to give programmers Moore's law's improvements, and so kind of these trickle up back into the program, and then you're stuck dealing with them.
Lunch ain't free anymore, right?
Yes,
yeah,
exactly.
Shocking. Right.
Okay. All right, let's let Ethan get a question in here.
It's not free. Ethan Miller, UC Santa Cruz. So just to follow up on what it was said, and what I was going to ask is there something intrinsic about Optane that requires 256-byte blocks, or is that a decision of whatever type on Intel's part, or do we even know? In other words, there is something intrinsic about Flash. You have to, for example, write large chunks at a time in order to build it efficiently. Mm-hmm. Is there something like that about Optane, or is it just this is the structure we designed, or do you not know?
I mean, I'm an assistant professor at CU Boulder, right? Like I'm not an Intel employee. It seems that there is, right, so it's a trade-off about, how much address indirection, or how much space you're going to put for address indirection. So this seems to be part of it. We also need to encrypt it, so we need to decide at what size we're going to do this encryption. I suspect that it would be hard to make the block size match cache line, because to me that seems like the obvious thing, and then you're kind of integrated across the entire memory system, and then you don't have these things. So, conceivably in future generations we'll get there, but it seems like at least for right now we're stuck using this.
Just a quick point, of the two of those, encryption's easy. 16-byte blocks are standard encryption size, but address indirection, I agree. If you have to do that on every block, yeah, I can see why it's 256.
Sure.
Hi, Juan from Amazon. I know your focus is on performance, but do you have any idea of failure rates of these devices?
So that's a good question. All I can say is we had access to this machine for 6 months, and we had students hammering on it for a long period of time. And if there were any failures, they didn't trickle out to our awareness. So that's the best statement I can make on that.
Thanks.
Yeah.
Chun from Future Week here. A comment on that block device.
Sure.
When you think about it, the memory is also a 64-byte block device.
Sure.
My question is on the where's the bottleneck? For example, we know that the Optane DIMM is much slower compared to DRAM. But does that mean that if Intel changed the memory controller or the Optane controller in the next revision,
yes,
then how would that change the paradigm?
I mean,
on the landscape.
Yeah, so that's a good question, right? So like Intel could come out with some totally different microarchitecture for controlling Optane in 6 months and could make this entire paper irrelevant. At the same time, this is the generation we have now. And it does seem like at least the block size being larger than the cache line and the interleaving effects are something that are likely to carry on, at least in my opinion, because if they were easy to solve, they would have been solved already. But it's conceivable, and we do know that the memory controller was redesigned to integrate Optane, right? So there has been some thought about these things, but to what extent, this is going to change in the future, that's unknown. Yeah.
So while the next speaker is setting up, I actually had one follow-up.
Okay.
Here, let's let her get set up. So it seems to me that there's some, like with Flash, there's some overhead to providing this fine-grained translation, right?
Sure.
And some people care about byte addressability, and some care about speed, and some care about both, right? But do you have an intuition about if I didn't care about the granularity, and I'm willing to shoehorn my writes and reads into whatever size is going to perform best, is 512 the right size? Or what size should the granularity be here?
I mean, so there are Optane block devices, right? So if that's something that you want, you can have an Optane PCIe device with 4K blocks. If that's what you're saying.
No, I'm saying, I guess I would say if I'm willing to shoehorn my workload into whatever size is best for Optane, what size would that be? You don't know? All right.
No idea.
Fair enough.
Yeah.
We're looking to have some interesting papers to look forward to. All right, well, let's thank our speaker one more time.